The purpose of this lab was to observe the motion of an object experiencing the forces of gravity and air resistance that was dropped from rest, and, using Newton's second law to predict its velocity and position, construct multiple computational models with different methods of calculating the drag force to see which modeled the experimental data most accurately. I recorded a video of my roommate dropping a flat plastic circular headphones case and tracked its falling motion over a little less than a meter. Then, using the mass to calculate the force of Earth's gravity on the object, I used Newton's second law to create a model in VPython, which predicted its motion without taking the drag force into account. This model overpredicted the displacement of the object, indicating that there was a significant force opposing gravity. I used 3 different estimations for drag force, and found that while all 3 predicted the data fairly well, the constant air resistance was the most accurate model. I placed the origin of the coordinate axis at the point where the object was dropped and plotted its motion along the negative y-axis in Tracker for about half a second. To construct the model in VPython, I initialized the variables for the object's mass, which I measured, the initial position of 0, and initial velocity of 0 since the object was dropped from rest, and then used the magnitude of the gravitational field near the Earth, 9.8 meters per second squared, to calculate the force due to gravity on the object. Throughout this lab, I made an assumption that the only 2 significant forces on the object were the force of gravity due to the Earth and the force of air resistance, or the drag force, both of which acted in the y direction. In order to use Newton's second law to predict the motion, the net force on the system needs to be known. I set the variable for net force to be the sum of the gravity force and the drag force. For this first model, I set the drag force to be 0. I used a derivation of Newton's second law. Final velocity equals initial velocity plus the product of the net force and change in time over mass to predict the changes in velocities over small time steps repeatedly using a while loop. Since the length of the time steps were small, 0.01 seconds, I could use the new velocity at each iteration to estimate the new position of the object, using the formula final position equals initial position plus the product of average velocity and change in time. When I plotted these results on the same graph as the observations, it was evident that the gravity force was not the only interaction occurring between the object and its surroundings, because the magnitude of displacement in the model was greater than that of the observed data. This meant that the net force had to be less than the force due to gravity, which indicated that the drag force opposed the force of gravity, as was expected. Because air resistance depends on many factors, such as surface area and velocity, there was no definitive way to calculate its force. I used an estimation in which the force of the air resistance was proportional to the square of the object's velocity first. In order to determine the appropriate A value, I used the model that matched the initial and final observed data point most closely. These data were not perfect, but the greatest deviation was less than a decimeter, a lot more accurate than the no-drag model, which at its greatest discrepancy was almost half a meter. However, I decided to try using a different estimation for the drag force that was proportional to the velocity to see if it was more accurate. I found that the graph of this estimation was very similar to the first approximation. The first and last data points were accurate, but there was a slight discrepancy in the points between these. Finally, I constructed a model in the same way using a constant drag force. The data generated with this approximation matched the observed data extremely well, as can be seen by this graph. When looking at all 4 estimations on one graph, it is evident that the second and third models are very similar. Both of these models share the characteristic that they are not exactly parabolic. Over time, their slopes approached a more linear trend instead of a quadratic one. This indicated that they were approaching terminal velocity, the point where the force of air resistance equals the force of gravity, so the velocity does not increase further. Observing the velocity versus time graphs of all 4 models, it is evident that only the second and third approach a constant velocity in this short time frame. The model of drag force proportional to the square of the velocity showed the greatest trend towards a constant velocity. The no-drag model shows no evidence of approaching terminal velocity, and the constant drag model could be flattening out, but there is not enough data to be certain. On the same topic, it could be noted that even if the object were thrown instead of dropped from rest, it would approach the same terminal velocity. To confirm this, I constructed models with various different initial velocities using the drag force estimation that showed the greatest trend towards terminal velocity, that which was proportional to the square of the velocity. As can be seen by this velocity versus time graph, all of the various initial velocities approached the same constant velocity of minus 2.3 meters per second. Overall, though the data was fairly accurate, it needs to be remembered that the motion was only observed for 0.47 seconds because the object was dropped from such a low height. If the falling motion were analyzed over a longer time frame and dropped from a greater height, more conclusions could be drawn as to which model was actually more accurate, whether or not the object reached terminal velocity, and how long it took to do so.